Welcome back everyone. In the last lecture we have started talking about the different components of the DSSC devices. What we have learned that there are 5 important components in a dye sensitized solar cell. The first component is an indium dot tin oxide glass substrate which is used as an anode material, and then the second component is an N type semiconductor. Usually we use titanium dioxide or the different structural form of it. Third important component is a dye or sensitizer molecule, and we have seen that there are certain parameters we have to keep in mind while choosing a dye or sensitizer molecule, like it has to have a very good light absorption properties, its molar extinction coefficient should be very high, it should not aggregate, and moreover its morphology and how it distributed over the semiconducting surface, that also plays a pivotal role. The fourth important component was the electrolytes. Now, the electrolyte actually is a major role in the DSSC device. It plays a major role because the electrolyte regenerates the whole process. Now, when the dye molecule get excited and goes from the ground state to the excited state, after some time it injects its electrons back to the TiO2 conduction band, and that electron using the percolated structure of the titanium dioxide goes to the photoanode and comes back to the outside circuit and complete the load. But what happens to the dye which has already lost an electron? So, it needs an electron, or in other way it has to comes back to the ground state so that it is again in a position of absorbing light again, and that work actually is done with the help of the electrolyte. So, that is why electrolyte plays a very important role in constructing DSSC device, and we have seen that. So, whenever we choose an electrolyte, so its viscosity not only matters, but also like its energetics also is very important, and how much volatile it is or how much corrosive it is, that also is a very important parameter. Now, today's lecture we will discuss about the different conditions for fabricating the electrolytes and how we choose an optimum electrolytes for a DSSC device, and at the same time what are the electrolytes which have been used in the DSSC device. For the redox couple, it should possess adequate thermodynamic characteristics to allow an efficient dye regeneration, as it determines the VOC values together with the semiconductor used. So, basically this electrolyte along with the semiconductor determine the VOC value of the device. So, it is very important to choose what kind of electrolyte we are picking up. Different types of mediators are used in the electrolyte, such as iodine triiodide we have used in the last class during the demonstration, SCN, SCN2, S2 minus and cobalt 2,3 complex among the most commonly used redox material. Now, popularly used redox mediator is iodine triiodide. Titanium dioxide N3 dye and iodine triiodide electrolyte that has been well studied and their energetics matches very well. Now, the characterizations of this or the good characteristics of this iodine triiodide material is that they show a very slow recombination kinetics with the electron injected into the TiO2 conduction band. Let us take a look about some frequently used electrolytes. For example, here we are showing 3-4 different columns. The first column is the solvent which we use, second column is the formula for that solvent, third is the melting point of that, fourth column is the boiling point, fifth is the viscosity, sixth is the dielectric constant, and seventh is the donor number. So, physical parameters of some frequently used organic solvents for electrolyte solution. For example, we can take this iodine triiodide electrolytes in ethanol, we can take in acetonitrile. So, what will be different if I take it in acetonitrile or if I take it in acetone, or how do I know in which solvent I will dissolve my iodine triiodide electrolytes. So, let us have a look at the properties of the solvent. For example, we have an universal solvent water H2O, melting point is 0 and we all know that its boiling point is 100 degrees Celsius and the viscosity is 0.89. Dielectric constant of the water is 78 and donor number is 18. Then look for the ethanol which has a molecular formula of CH3CH2OH and it has a melting point minus 114 degrees Celsius, boiling point 78 degrees Celsius, and its viscosity is higher than the water 1.08 and dielectric constant is lower than the water 25. So, that is why it is less polar than the water and donor number is 29. Then another common example, we have dimethyl carbonate, we have diethyl carbonate, we have acetonitrile, which we use very commonly. Acetonitrile is represented by the formula CH3CN. Now, it has a melting point of minus 44 degrees Celsius, its boiling point is 82 degrees Celsius and its viscosity is 0.33 or 30 degrees Celsius. At 30 degrees Celsius its viscosity is 0.33. So, you look that its viscosity is lower than the water. So, that is why it is good to make the iodine triiodide electrolytes in the acetonitrile solvent, and dielectric constant is 36 and its Donner number is 14.1. Similarly, you can choose propyl nitrile PPN, butyl nitrile, valeronitrile or glutaronitrile. So, all is changing is the number or the amount of the alkyl group in front of the CN or cyano group. So, based on that we change the name propyl, butyl or valero or glutaro. In the case of glutaronitrile we will have NC group also. So, there are 2 cyanide group and in between there are CH2 group is there, and then there are 3 methoxypropanitrile or MPN group, and finally ethylene carbonate. Ethylene carbonate has a melting point of 36 and a boiling point of 238, quite high, and its viscosity is also very high, 90. So, that is why it is not very suitable for making this kind of electrolyte solutions in them, and dielectric constant is very high, 90, and its Donner number is 16.4. So, if we look at this chart, so some of them has some properties very good and some of them has some other properties very good. So, if I keep everything as a optimum from this table, it looks like acetonitrile plays a role where have a ideal melting point and ideal boiling point, viscosity is also very low and the dielectric constant is moderate. So, that is why we prefer the acetonitrile as a solvent for dissolving this iodine triiodide electrolyte. Special aspects are essential for the electrolytes used in DSSC. The electrolytes must be able to transport the charge carriers between photoanode and counter electrode. So, it will be able to carry the charge from the photoanode and the counter electrode. After the dye injects electron into the conduction band of the TiO2, the oxidized dye must be rapidly reduced to its ground state. So, the role of the electrolyte as we mentioned is to reduce the dye from its excited state to the ground state. Thus, the choice of the electrolyte should take into account redox potential and regeneration of the dye and itself. Many times choosing behind the electrolyte molecule depends upon its cyclic voltammetry based HOMO-LUMO level. So, first we need to measure the highest occupied molecular orbital and lowest unoccupied molecular orbital of this redox couple by cyclic voltammetry experiment to see that whether it will be suitable to make the redox couple. The electrolyte must have long term stabilities including chemical stability, thermal stability, optical stability, electrochemical stability and interfacial stability. So, by chemical stability we mean that this electrolyte solution should not degrade in its constituents atoms or constituents molecules. Thermal stability means if we increase the temperature it should not be very volatile. I mean most of the case these are volatiles. So, that is one of the disadvantages of the DSSC device. Its optical properties should be moderate, its electrochemical properties should be good so that the energetics matches well, and also the interfacial stability is very important, because in most of the cases in the solar cell device interface plays a very important role. Now, these electrolytes also are there in the interface of the dye molecule and the counter electrode. So, that is why its interfacial stability is also very important while we construct the electrolyte solution. Finally, it should not cause any desorption and degradation of the sensitized dyes. Obviously, we have to be very careful that whatever the dye we have chosen and whatever the electrolyte we have chosen, they should not interact or chemically react between each other. Otherwise, the new complex will be formed and whole things will be changed. The electrolyte must guarantee first diffusion of the charge carriers or higher conductivity and produce good interfacial contact with the mesoporous semiconductor layer and the counter electrode. So, now these electrolytes are there at the interface of the TiO2 layer and also at the platinum counter electrode. Now, their interfacial stability or the interfacial properties with the TiO2 layer and the platinum counter electrode should be very good, and at the same time they should express a very fast diffusion of the charge carrier. That means their ionic conductivity should be very high. The electrolytes should not exhibit a significant absorptions in the range of visible light. Now, if the electrolyte absorbs most of the light in the visible range, then it will be problematic for the whole device. Since the iodide triiodide redox couple in the electrolyte shows color and reduced visible light absorption, that is why it is a preferred choice for making the DSSC device. In iodide triiodide redox couple, triiodide ions can react with the injected electrons and increase the dark current. So, the concentration of iodine triiodide must be optimized. Now, we can also classify the various kinds of or the various types of the electrolytes in a DSSC device based on their physical state, whether they are liquid state, whether they are solid state, or whether they are in between liquid and solid, that is quasi solid state. So, you look this pie chart. So, we have this ionic conductor, we have inorganic whole transport material, we have organic whole transport material in this pink color shaded regions, then we have organic solvent here. IL stands for the ionic liquid solvent, iodide, triiodide free and iodide, triiodide. And here we are showing thermosetting P, quasi solid IL, thermoplastic P and composite P. IL stands for ionic liquid, HTM stands for whole transport material and P stands for polymer electrolytes. So, we can use also the polymer as an electrolyte, or we can dissolve the polymer in a proper solvent to use it as an electrolyte. The liquid electrolytes possess some important features such as easy preparation, high conductivity, low viscosity and good interfacial weighting between electrolytes and electrodes, and thus high conversion efficiency for the DSSC. Now, these are also the design parameters for the electrolytes. First of all, they should be easy to make. If we make this thing from the iodine triiodide in the acetonitrile, so the synthesis is quite easy. They should have a high conductivity, their viscosity should be low, and finally, their interfacial weightability with the n-type semiconductor oxide and the platinum counter electrode or whatever electrode you are using, that should be very good. Now, if all the parameters are optimized, then we get a higher efficiency in this DSSC device. But the use of liquid electrolytes poses some practical problems due to solvent leakage or evaporation, which could negatively affect the long term stability of the device. Now, these liquid electrolytes, they are volatile and corrosives. So, they evaporate over the time. So, if it evaporates, so let us say I put some drop of electrolyte in my devices. So, if I do not seal it properly, after some time the electrolyte will evaporate. So, nothing is left in the devices to regenerate the whole process. Now, the electrolytes intrinsically shows the properties of the volatility, that I cannot get rid of this thing. So, that is one of the major disadvantages or the drawback of the liquid based electrolytes. The use of the quasi solid or solid state electrolytes could be the answer to these problems. So, that is why people are trying to replace the liquid electrolytes with the solid state electrolytes or quasi solid state electrolytes. Quasi solid state electrolytes become viable alternatives to the liquid electrolytes owing to the improved stability and better sealing ability. So, as I said that the DSSC device has to be sealed properly, otherwise the electrolyte will be volatile, it will be evaporated. So, now if the volatility we can control in the solid state electrolyte, then that is advantageous for us. So, that is what is done exactly in quasi solid state electrolyte. Quasi solid state electrolytes or semi solid state is a special state of a substance between solid and liquid states. Quasi solid state electrolyte is a macromolecular or supramolecular nano aggregate systems characterized by a remarkable ionic conductivity. So, quasi solid state electrolytes usually have a very high ionic conductivity value. Quasi solid state electrolytes always possess both the cohesive property of a solid and the diffusive properties of the liquid. So, they get both the good properties of the solid. So, solid shows a cohesive properties, all the molecules in the solids are very tightly bound. At the same times, they show the good properties of the liquid. What is the good properties of the liquid they are taking? That the diffusion. And quasi solid state electrolytes show better long term stability than liquid electrolytes and have the merits of liquid electrolytes including high ionic conductivity and excellent interfacial contact properties. Now, let us have a look about the transport mechanism of electrolytes in a DSSC device. In the electrochemical circuit of DSSCs, the electron transport through TiO2 crystalline film and the holes transport through electrolytes or hole conductors. So, even if I use a conducting polymer which is a very good, which has very good hole conducting properties, so that will also act like a good sensitizers as well as a good hole transport material. So, the final objective should be to design a material which can replace my sensitizers and the liquid electrolyte by only one material which can absorb both the light and also can behave as a hole transport material. Electrolytes or hole conductors are hole transport mediators. The basic function of electrolytes or the hole conductors is the regeneration of the dye and itself in DSSC device. For typical iodide triiodide redox couple electrolytes, the regeneration of the dye can be expressed by the following equations. Here you have the dye which is in an excited state. So, D plus, that is what we mean, and then iodine minus. So, the iodine, the dye in the excited state, they grab an electron from this iodine. So, it becomes neutralized and it becomes now the only D, and the iodine now it has donated its electron to the dye. So, it is becoming more negative. So, I 3 minus. The reaction contains a series of successive reactions on the TiO2 interface. D plus I minus is Di complex. In the presence of more I, it will become D plus I2, and finally it will become D plus I3 minus plus I minus. So, both of them coexist together, and this is a dynamic process. So, D plus I2 minus is equal to I2 plus D, and finally you get D plus I3. The regenerative cycle of electrolytes is completed by the conversion of triiodide to iodine ions on the counter electrodes. So, finally, what happens? So, iodine has given up its electron to the di molecule, and di molecule has been reduced back to its ground state. Now, once the iodine has given its electron, so it has converted to more negatively charged triiodide. Now, if the regeneration process has to happen again, so not only di needs to be regenerated, this electrolytes also needs to be regenerated. That means we need to have iodine in the system from the triiodide, and that job is done at the platinum counter electrode. So, where the triiodide is converted to the iodine, and this process cycles. So, today we have learnt in details about what are the different varieties or the classes of the electrolytes, and what are the properties or whatever the design principles for choosing a right electrolytes in a DSSC device. Because for optimizing efficiency in a DSSC device, choice of electrolytes is also very important, and the final objective should be replace both the sensitizers and the electrolytes with only single material, preferably a solid material, which can absorb the light in the visible region as well as in the near IR range, and at the same time and work as an electrolyte material with a very high ionic conductivity and a very good weightability at the interface of the semiconductor as well as the counter electrode. Now, we have seen that although there are several choices of the electrolyte, still iodine triiodide electrolytes is commonly used with the N3 dye because they make a proper energetics. But the lot of research is ongoing to make new kind of solid state electrolytes, because the solid state electrolytes possess the diffusive properties of the liquid and also the cohesive properties of the solid, and they retain all the properties of the liquid state electrolytes like excellent ionic conductivity and good weightability. But at the same time, it is not very easy to make a good solid state electrolytes depending upon this energy level matching and optimizing all the parameters. So, there are research are ongoing, and every day we are coming across with the new materials or new electrolytes, but finally the major advantage or the major leap in this technology will only possible if we can make all solid state devices. Then we can seal it properly and we can make roll to roll devices. Now, for this particular chapter, this based on the dye sensitized solar cells, there are a lot of references and lot of research papers are available. Especially you can look for some of the papers or some of the books like metal free organic dyes for dye sensitized solar cells from structure, property, relationship to design rules by Amresh Mishra. In this book actually they have talked about like the design synthesis rule for the metal free organic inorganic dyes, and there are a lot of research papers also available on that. Optimizing dye for the dye sensitized solar cells by Neil Robertson. Here they have talked about like different kinds of dye molecules in the dye sensitized solar cell. The renaissance of the dye sensitized solar cell by Smith and Maggie. Organic sensitizers for dye sensitized solar cell DSSC, properties from computation, progress and future perspective, and electrolytes in DSSC, and that was a book by Zhang Lan. So, any of the reference will be useful, and apart from these books there are a lot of research papers and review papers are also available, which gives in details about the photophysics and working mechanism of a dye sensitized solar cell, and how to choose a proper dye and how to choose a new electrolyte material for constructing a DSSC devices. In the next lecture we will talk about another class of solar cell, another class of the third generation solar cell, that is the organic solar cells. Dye sensitized solar cell was an example of a sensitizer based solar cell, where the organic solar cell we use conducting polymers as a electron absorbing material. So, not only an electron absorbing material, we also will see there the physics will be completely different, or the charge carrier dynamics will be completely different from a PN junction silicon solar cell to an organic solar cell. That we will learn in our next class. Thank you very much.